Welcome to Problem Solving with Miss Jones. I've gone ahead and listed everything that was given in the problem. We know that it starts at an initial velocity of 0 and it gets up to a final velocity of 5 times 10 to the 7th over a distance of 1.2 centimeters, which I have converted to meters. And the question is asking for the electric field. So here's where we might get stuck because there's not a lot of information given relating to electric field. You should have this equation, E equals K Q over D. We have a distance and we have a charge, but this is an external field, not created by this particle, so I'm not sure that's going to work. Another equation you should have with E in it is F equals EQ or QE. So what we should notice is that this electric field is causing a force that's going to accelerate this particle. So what we need to do is combine this with F equals ma, Newton's second law. So if we just combine these, EQ equals ma, or E equals ma over q. And this is the equation we're going to use to solve this. Now, at first glance, it might seem that we don't have any of this information, but there's one given that's missing from this list, and that is that this is an electron, and electrons have a mass of 9.11 times 10 to the negative 31 kilograms, and they also have a charge of 1.6 times 10 to the negative 19th. So that's how we're going to get the mass and the charge. The next thing we need to do is solve for acceleration using the constant acceleration equations. So if we want acceleration, we have velocity initial, velocity final, distance. Nothing about time is listed in this list of givens, so we want to use the equation without time, which is vf squared equals vi squared plus 2ax. So I did the substitution and the algebra to rearrange this, and I got a pretty large acceleration of 1.04 times 10 to the 17th meters per second squared. So now we have everything we need to substitute into this equation and solve for electric field. So here's the substitution for the electric field, and when you do that, you get 5.92 times 10 to the 5th newtons per coulomb. Now let's talk a little bit about the direction here. I didn't include the negative sign on this charge of an electron because when we use this, we're using the absolute value of the charge, so that should be included in that equation there. And then the direction of the field, so in order to slow this down, I drew it going to the right. In order to slow it down, it must apply a force to the left. Remember, electric fields tell us what would a positive charge do. So if this field was to the right, that would speed up a positive charge to the right, but it would slow down a negative charge moving to the right. So the force on this negative charge is actually going to be to the left. So if it asks for the direction would be to the right with your electron also moving to the right.